Okay, so let's get started. So I've posted a couple of project ideas. I'm maybe waiting for one more idea, but what I will go tonight and do is assign teams with some topics. Unless somebody says, I want, I'm really attached to a particular topic, I'll do the random assignment of those topics. But if somebody really feels that I'm really passionate about a particular topic, then just let me know. We can figure that out as well. Okay. And I'm thinking like, so let's say we have 15 teams, right? So I think four topics, one topic will be done by four teams, same project. You can get innovative. I mean, you can have different approaches as a team. But what we will do is maybe make a competition. Like we will have three awards for the final project. First award $200. Each person gets $50 Amazon gift card. Uh, First prize. That's the first prize team. Second prize will be, let's say, $100, $25 each Amazon gift card. Third team will get a, let's say, $40 gift Subway gift card. You can guys can go out and eat a Subway with. So there will be out of 15, there will be three awards that we can select, something like that, just to pump you guys up. Okay. So okay, let's let's get started then. Yeah. So we are doing PID controllers, right? So now we have discussed in previous three or four classes about setting up like first order and second order transfer functions. You can find higher order transfer functions. So basically, the idea is to either it's a state space or a differential equation, use Laplace transform to get it to S domain, and then just basically find a ratio with initial condition zero, ratio of output versus input, right? So that's the idea. Now, the idea is that, okay, you have a, a plant is given to you or a system is given to, and you have a transfer function. You cannot do much with it, right? Whatever response it will give. All the response is dependent on the location of poles, which are the roots of the denominator, right? So now the idea is, what if you don't like that open loop transfer function, or if you want to change it? That's the idea, right? Because the idea is, okay, we understand the given system, but now we want to modify it. We want to control things. We want to track a particular trajectory, or want my aircraft to hold a particular attitude or a roll angle or a pitch angle, right? So what kind of controllers we can do? So that's what we are doing here. PID controllers basically are applied to first order, second order systems, and basically they change the location of poles. That's the whole idea. So whatever the poles are locations are given to you, you get a better location, desired pole location. Okay, I want my poles of the system right here. So how can I move it there? What kind of control technique I can apply to? So this is a very intuitive, very simple controller, but sometimes choosing the gains can be a pain in the butt. So uh, people struggle a lot of like all the like last year when this assignment was done, people said we spent like several hours just tuning the gains for the autopilot. That was the kind of story I heard from several people. So, but if you apply a educated approach of choosing gains, you can at least get a good guess, so that you won't have to tune that much, right? So most of the times when I applied that, 5 or 10 minutes, give and take, we were able to get gains, which were, so we will go over the techniques, how to choose gains first, at least if things are idealistic, what will be those gains, and then that can be the starting point. Okay, so so as I said, PID controllers can be basically made up of three type of controllers. Basically proportional, so that's proportional. Uh, so that's proportional, right? And the idea is very simple, right? So this is your open loop system here, right? This is the given system to you. And so the transfer function is what? A ratio of y over u, right? That's the transfer function we have, or your plant. It does not have to be a transfer function. It can be a state space, whatever system given to you. And the idea is, okay, I want to give I give a u, you get a y. But we want to move forward, right? We want to say, no, I want my y to track a reference input, right? Or track so I want it to be a desired output rather than just any output. Okay, so this y can be your phi, which is roll angle in the aircraft. So you want it to track a reference phi, so okay, 30-degree roll, hold that, right? So this here is that. So you want your output y to go to y reference, right? So then what's the error then? If you are not there, that means there is some error between y and y reference. So that's what we call it error, E here. That's the error here, right? So E is nothing but y reference minus y. So this is what you want your output to be, and this is your actual output. So there is an error. Okay. So now the simplest controller is multiply this error with some gain kp and plug it in as an input to the system. So that if there is an error, there will be, so basically what the u coming out of this, so now our u equals to kp into e. So that's your proportional controller basically. Okay, that's in simple terms of proportional control. So you are applying control effort proportional to the error so that that error can go to zero. So if large errors initially, you'll get a large input. If you have small inputs initially, so if you can think, let's say you are going from this point to this point, right? If initially you will go towards the target at a high speed, but as you reach, you will really slow down. Like it as t goes to infinity, you will reach there. Kind of argument will happen. So, but that's the basic control. If so, it always tries to minimize this error or make this error goes to zero. That's the idea of proportional control, right? How far? So the larger this gain, the faster you will reach. But there will be overshoot, right? You will have a momentum, and then you will overshoot, and then you will come back, and so you will have a, like, if you want to track this trajectory, you will have get something like this. Okay, so that's the proportional controller. Okay. So the next controller is the integral controller. So there will be systems, and we can discuss that when we get some transfer function. Let's say I want to, that's your y reference, right? So when you go a reference, even after applying any proportional or any controller, you have some steady state errors, right? So the reference state never tracks so the actual output never tracks the reference output exactly. There is small errors, 0.01 point. But if you see this error, the area under this thing, when you start integrating, the error accumulates, right? So the integral control, basically what it does is you apply control proportional to that accumulated error. Okay, so the objective of integral control is basically to get rid of steady state errors. Okay, and we will see that integral control generally increases the order of the system, because if you take the Laplace of this, it will be 1 by s. Okay, so 1 by s, when you add in the denominator, the order of the system increases, and that sometimes is not good. So we will give you some techniques, like if you are doing inner loop control and if there is no steady state error, it's not a good idea to apply integral control. Okay. And next, so this is integral control. Basically, it will be u equals to, if I write into that, like integral of error e dot dt from 0 to t into ki, right? So basically, ki is the gain multiplied by that error accumulation. So that's your u. Again, you can apply kp, this PID, because it's called PID because you can apply any combination. You can just apply proportional controller. You can just apply integral controller. You can just apply a differential controller, or you can apply a combination of them, PD, PI, or PID, all three of them together as well, depending on what is the requirement in hand. Okay, we'll discuss that as we go on. So the third one is called derivative controller, which basically is saying, so you want to control the speed, how fast you're moving, right? So you want to provide some kind of damping. Like see this here takes it directly with full force towards the goal, right? But you want to have some control on how fast you go towards that. So you want to apply input which is proportional to that rate of change of the input, right? Or the error. So this is KD into E dot basically. So this U, when you just apply U, will be KD into E dot. What is E dot in this case? Y reference is constant. So if E is this, what will be E dot? What will be E dot here? Rate of change of error. If Y reference is constant, what will be E dot? Guys, differentiation. If this is my E and Y reference is constant, what will be my E dot? No, not zero, 0 minus Y dot. Okay, so basically this is equals to minus KD into Y dot. So rate of change of the output Y dot. Okay, so sometimes if E is not there, you will all can be confused. Generally, it's proportional to the error dot. If you had a if YR was changing, right? If YR was some kind of a change, like a time varying input, then this won't be the case. Then you will have YR dot minus Y dot. But if you are tracking step input or a constant input, then in that case, it will be equal to that. Okay. So, so we'll see how applying a combination or a single of them changes the transfer function, right? Now, so now the transfer function will be, what is the input now? So in earlier system, your input was U, right? So the transfer function was a ratio of Y over U. But now the input is Y reference. You will have to find a transfer function from Y to YR. Okay, because now Y reference is the input to the system. So that's the closed loop transfer function we are talking about. Okay, Y to Y reference rather than just Y to U. We are saying because U is the internal command now, U is computed based on, so YR is the reference. So what the transfer function that we will be talking about, which is the closed loop or closed loop transfer function, so it will change because now if you see, once we do the math, the transfer function will be a function of the the actual transfer function, which is the open loop transfer function, and Kp and Kd and Ki's. We'll see how. It's not simple ratio finding, nothing big. Questions here? Anything? Anybody has a question? Okay. Are you so? Anyway, what you see what we are doing here? We are trying to make this error go to 0. Simple. We want our Y to track Y reference. And to do that, we are using this 3 type of controllers or inputs which are proportional to error dot, and accumulated error. That's all. And when we do that, basically the closed loop transfer function changes. And we'll see how it does. And then we can choose those gains to satisfy our closed loop transfer function requirements. Okay. So basically, and then you can actually, as I said, you can apply all 3 of them together. So this is how it will look like. So you have a proportional, you have integral, and you have a derivative controller. All 3 of them applied together will, okay. As I think we have already kind of discussed these important concepts, but PID is one of the most used controller till the date in all the awesome systems that we have, like Airbus, Boeing, all these aircrafts uses PID till date. Okay. So again, let's just see how those 3 controllers are acting. So this, if you see this first part of the, so that's the Y reference here, right? And so that's the proportional controller acts on the distance from the reference command. So how far you are from the reference command. So you basically, this pushes you towards the reference command. Derivative control acts on the rate of change of the error. So on the slope. Okay, so basically you can determine the slope based on that. An integral controller acts on the steady state error between uh, the tracked error and all. So this basically summarizes the need of all the three different controllers. Okay, so let's take a simple example here. So let's say I have a plant here. I'm just discussing PD control for now, just no integral. As I said, integral control is needed when there is a steady state error. So you have to first determine if there is a steady state error or not. But if it is there, then so what will be the ideal? Like if I don't know if you remember from last class, there was a DC gain or final value. So what is the ideal situation you want from a transfer function YR? So it is Y over YR, right? That will be our closed loop transfer function. What should the final value look like for this? Or DC gain look like for this? One, right? If the final value or the DC gain of the closed loop transfer function is one, that means at steady state Y will be equal to YR, right? If that is not the case, then there is steady state error. So we'll see. Uh, so now let's say this is our open loop transfer function, which is a standard B0 over S square A1S plus A0, right? So that's the open loop transfer function. And you give an input, you get an output. So that's our open loop transfer function. We can find our poles, okay? Uh, so I will also later on show you technique. You don't even need to find poles sometimes, but we'll so that's our open loop characteristic equation. What is the characteristic equation? A denominator equated equal to zero, right? So the roots of this equation, open loop characteristic equation, are the poles of the system. Okay, so your poles are just it's a minus b by 2 plus minus b square minus 4ac. So you just a standard quadratic root solution here, right? So now depending on what is A0 and A1, these poles can be both positive, both negative, one positive, one negative, or imaginary, right? Depending on what A1 and A0, the relationship between A1 and 0 for now, but they are the open loop poles. Okay. We will take a numerical example which will show you whether system is. So if the poles are in the left half of S plane, like something like this or something like this, then it's a stable system, right? Open loop system is stable, otherwise it is not. If anything goes in this area, we are toast. But after after we apply the feedback control, we can bring those poles back. We can drag them and bring them back to the uh, uh, left side, right? So my question, so that's the case. So what we want to do is now we want to, so first objective should be compute the new transfer function, which is the closed loop transfer function, YR, Y over YR. How can we do that? Okay, if you can somebody suggest how will we do that? So if you see here, like little math, so first let's just compute, the basic idea is compute U of S. What is U of S? Because Y of S, if you see, is equal to this transfer function, right, B0 over S square plus A1S plus A0 into U of S, right? That's the case. Now I think this from here we can compute U of S and then just multiply to it, right? And then go and find out the ratio of Y over YR. Okay, so what is U of S in this case? Any ideas? So if you see U of S is made up of two parts. One is Kp into Y minus Y reference, right? Or Y reference minus Y. Oh no, so this will be all will be S here. And minus Kd into Y dot. So the Laplace of that will be S into Ys, right? S into, see, from here when it goes, it takes, when you do E dot into Kd, basically uh, KdS into Ys, right? So that's my U of S. that I can substitute here and then solve for a ratio of y over yr, because u of s then will be eliminated, right? Everything will be then yr and y, and you can find a ratio of the transfer function. So so that will be the case. Oh, okay. So y reference minus y reference minus y. That will be clear here. So it's like this. So all we have to do now is just, because now everything is replaced by we have to just now, you can just separate yr, ys things, and basically the new ratio will be, so ys over yr will be this new transfer function. Nothing major going on here. You are just separating terms with respect to yr, collecting coefficients of yr, collecting coefficients of y, and then taking the ratio. Okay, so this is the new transfer function we have. This is the closed loop transfer function, which is the ratio of y of s over y reference s. Okay, got it? So now you see kd and kp is appearing in both the numerator and denominator, right? Right. So now we can see, so the order of the system did not change. The order is still the second order transfer function. So what our open loop was, if you see, our open loop transfer function was this, and the closed loop transfer function is this. So you will see that your kd and kp appears in the coefficients of the. So now you can go ahead and find the roots of the closed loop transfer function, right? So so the poles, or the solution of this equation, will be the poles. So our new poles. So this is your closed loop characteristic equation, and these are our new poles. So now if you see, you compare these poles with the desired poles. What, for example, let's say I want to place my eigenvalues or poles at -3 and -4, right? So there are two poles. So basically the characteristic equation is s plus 4 and s plus 3. That's the desired one. So that is desired characteristic equation. This is what I want. So your pole is at -4 and -3. So now you can compare one pole equals to 4 and one equals to -4 and one pole equals to -3. Value of A1, B0, A1, B0 is given to you. Now you can basically, so two equations, two unknowns, you can solve for Kp and Kd. So you got your gains, which will place your eigenvalues of closed loop transfer function at -4 and -3, right? Or on, like, even if you don't, so solving this is a bad thing, right? I don't like taking square roots and all, but so what you can do is you can open this up, s square uh, plus 7s plus 12, right? So this is the closed loop characteristic equation. You can actually compare this with this equation. So basically A1 plus B0 KD should be equal to 7, and A0 plus B0 KP should be equals to 12. So from these equations two, you can just compare, rather than getting the roots, just compare the coefficients of the differential equation. Boom, you can get your Kp and Kd, so that it will place the poles at the desired location. Okay, and again we will see. I will later on we will discuss how do we choose where to place them. That's a different thing, but we can place. Questions here? Maybe let's do a Matlab thing and show you how the step response looks like, and then we move further. Questions here? Nothing? So the autopilot assignment will be not bad because we are using PIDs. It will be bad because how many PIDs you are using. So yes. Oh, so I said I want to place my poles at -4 and -3. These are the desired locations. So the characteristic equation then is s plus 4 and s plus 3. So those are the locations you want to place the poles of the closed loop transfer function. Okay, and we'll see how important that becomes, because sometimes your open loop can have poles at +4 and +3, and then you can drag them and make it a stable system, basically. So unstable system can be made stable by applying a controller. Okay, so let's see if we can. Let's go to this Matlab, and so I don't know if you have seen these commands of. So let's say I want to, let's just cook up a transfer function, right? What was our transfer function looking like? So it was B0 over, so it was B0. So let's just cook up a transfer function here. It was B0 over S square plus A1S plus A0, right? So there are three kind of, so how do you enter a transfer function in a MATLAB basically? So you basically, there is a command called transfer function in MATLAB. You have to give the coefficients of the numerator and you have to give the coefficients of the denominator. For example, in this case, so you always, so the numerator and denominator can be same. So the highest power is 2, right? The numerator cannot be more than that power. So it always has to be less than. So when I say numerator, you can be just put the coefficients. So the coefficients in numerator for s square is 0, right? For s is 0 again, and for the constant part it is b0. So that's the numerator part. When I'm entering the same transfer function, the denominator is equals to 1 for s square, then a1, and then a0. So that's how you enter a transfer function. Like first define the matrix or a vector for the numerator and denominator, basically. So let's say, let's pick up some values. Let's say b0 is 1, and s square a1 is 2. So, and this is 1 as well. Okay, something like that. So that's our transfer function that we want to enter. So if you see, I can say num, so assess equals to tf. So tf is the command, transfer function command that you can put, and you put the numerator first. So that will be 0, 0, 1, comma, then denominator, that will be 1, 2, 1, right? So if you do, you will see you'll get a transfer function, which is system is equals to 1 over s squared 2s plus 1. So that's the transfer function we have. Okay. So now if you want to see the step response of this, like you want to see how when you give it a step, does everybody know what a step response mean? Like when it's just one step command. So you are starting here and say, okay, go 30 degrees. So you basically give a constant 30-degree command to it. So it can start at t equals to 0, or you can start that step response at any place. So step response is basically a constant command given to. So if we don't have any figures, so you can do just step. We can do this in Simulink also, not a problem. I'm just showing you the command window thing. But so we already have a sys, which is a transfer function. So it will simulate the step input of 1 unity. So it says go to 1. The output should be 1. It will give you a figure, right? So the step response is this for that open loop transfer function. Okay. So I don't know if the questions here. So this is the step. You can see now you want to change. So I don't know. Let's see if we can see what are the poles of the system. Poles. sys will give me poles. No, let's say help poles. Poles or poles? Anyways, so this is, so what we want to do now is we want to place whatever the poles are. We can use like minus b by 2 plus minus b square uh, minus 4ac divided by 2, right? So b is 2 here and a is 1. You can plug it in and you will get the roots of the equation. So that's not important. What was our so that's the open loop transfer function. And the closed loop transfer function we had was, I think, what was that? It was 1 over s square plus 7. What was 7s plus 12, right? So that's the transfer function we have. So let's see how I want to implement it. I just want to show how, if we want to implement a controller first or want to show you how to choose the gains. So let's just go to Simulink so that we can actually implement a controller there. Okay, so we want to place, so that's the open loop thing, and that is the closed loop transfer. So we have open loop characteristic equation, which is s square plus 2s plus 1. And we have that's open loop. And we have closed loop is s square plus 7s plus 12, right? And if you see after we have applied the PID, we can compare the coefficients of which is what? S square, can you help me? S square plus A1 plus B0 KD plus A0 B0 KP, right? So, yeah, yes. So that's multiplied by S, yes. So now all we have to do is compare the coefficients of this with the closed loop thing. So we have A1 equals to, oh sorry, A1 plus B0 KD equals to 7 and A0 plus B0 KP equals to 12. So we can solve for, and what are A0 and B0? So B0 equals to 1, B0 equals to 1, and A0 is also equal to 1, and what is that? A1 equals to 2. So you can plug these numbers here and solve for Kp and Kd. So that will be 2 plus Kd equals to 7. So Kd equals to 5. And what is that second one? That will be A0 is 1 plus B0 is also 1 into Kp equals to 12. So Kp equals to 11. So our KP equals to 11 and KD equals to 5. So these are the gains. If you apply, you will get the characteristic equation to that. So let's implement this in the, let's see how you implement a PID controller in Matlab, Simulink. Okay, so that's our blank model. If you open the library, uh, commonly used blocks. So there is something, a place where you can put transfer functions. Transfer function, right? So this here, you can just drag here. So that's our open, that we can put our open loop transfer function. Okay, so if you double click it, so you can again same thing, like if you see our what are our open loop coefficients, it is of, so that's 0 0 1, right? So it will be, and the other one will be 1 2 1, right? So you can apply, so that's our open loop transfer function. Now, so that's the U comes in and Y it goes out. So we want to apply a PID controller to it, right? So so again, let's go back to our library, and we can have, so either you can apply this block, but I was thinking if I can just, so I have integrator here. So let's put first a reference signal, uh, commonly used block. So you can go and put a sum here, right? So the Y reference, so actual Y will come from here. So that's our Y, and your Y reference will go from, so maybe a scalar. Where is the scalar? Do you see a scalar here? Let me know. Maybe sources. Or you can use just a step input, right? So that's our Y reference. And so that's the Y ref. So we can change this because it has to be negative. So apply. So because we want to compute the error, right? So Y reference minus Y. So that will be your error. So that will be then multiplied by a gain KP. So if you see where will be, so a gain, so that's our gain. We can choose our KP here. So that's our, yes, we can write it this as KP. Okay. So that's KP. So that's error multiplied by KP, right? So what was KP in our case? What did we choose? 11. So we can put 11 here, apply. Okay. And then, so then we also need another one more summing. here, because that so KP comes from here, and we'll get the KD also from here. So for KD, we need minus KD into S of, so let's see if there's a differential function which can give me a, so 1 by S is there. Do you see a differentiator? I'm doing it first time implementing PID in a Simulink. So sync signals continuous. One by S. Will this be a derivative? No. Let's Google it. Derivative and Simulink. So this is also like, it also raises one good point here. Like when you are actually implementing things on an autopilot, and when you have a single board computer that you are using on board your UAV or unmanned, you will not have Matlab there. Okay, so you will have to come up with functions that can do derivative job, and integral job. Here we are pulling things out. So that also we will learn when we are doing the autopilot, that how do you actually implement a PID on a computer without Matlab, just on single computer. So that we will be learning that. But here I was thinking if I can get a, maybe just use a transfer function thingy. So let's say, any ideas? Maybe just use the transfer function such that we get a S. So let's see, control C, where is our, so if I say control C, yes, I can use the PID block, but I'm thinking, so it will be, nah. Let's use PID for now. Well, I'll get back to you guys how to get a transfer function. So I think I know where I can find it. Sorry, guys. Airspeed from pitch or course loop, roll loop. Okay, 1 over S. Ah, so actually there is nothing. You actually need to get a theta dot. So let's for now use a, because I cannot separate my theta PID. So it's, what is that, 11, and what is the derivative? Derivative is this 5, right? Apply. So the problem is, because we are getting directly the output y, right? I need a y dot. And it seems like in Matlab there is no s derivative function that you can multiply to it and get a theta dot type of thing. So for now, we'll just use a PID. We don't need this here. We don't need. So it's doing the same job, but I wanted to. Okay. And let's add a scope to see how the response looks like of the y. And the step input is step time 1, initial value is 0. Okay. So let's make it final value to be 5, maybe. Apply. Okay, so let's run it. So you'll see it has steady state errors. So it seems like we will have to use a PID. But you see, it starts here. But it's because the step input was applied at time t equals to 1. And we went close to 5, but we never reached 5. So there is a steady state error here. So if you see, if I put an integrator here, which of course we did not derive here, but randomly if I put an integrator, it should improve, let's say 1. Little, did it improve a little bit? A little bit. So if we increase that again, because since if we would have put the integral and derived the equation, we would have a direct solution of ki there as well. But so yeah, so you see the integral kind of works its magic and provides correction based on that steady state error. So we will continue that in the next class, where we will take a actual example, apply PID to our inverted pendulum problem. So we will derive, apply, and try to make the inverted pendulum stabilize. So that will be our next problem. And then next week, we will jump on the autopilot design, where we'll get transfer functions for the UAV, different loops. Okay. But this will be the approach. You put a transfer function, you apply the comparisons between coefficients, you get your gains. That is your starting point. And then basically play with your transfer function that without even applying to the simulator, first you tune your gains in using this Simulink approach. Just put your transfer function and see if your gains are good enough to at least give you the similar response in a separate Simulink file, and then go ahead and apply that to the simulator. So that will be the kind of design approach we will use.